Assalamu alaikum. Good evening. Bismillah ar-Rahman ar-Rahim. In this part of the lecture, we are going to finish discussion or our discussion about differentiation and actually about application of derivatives. We are going to consider what is called L'Hopital rule. L'Hopital rule is a simple yet important rule to solve the problem of limits using differentiation. We start this lecture with a quick refreshment about limits and then consider L'Hopital rule in its basic form and then turn our attention to some other cases that can be solved also by L'Hopital rule by making some mathematical manipulation first and then apply rule. Let's start with a quick refreshment about limits. What is the meaning of limit and what is the mathematical definition of limit? The limit of a function is to consider the behavior of the function at some point that cannot be determined using algebraic substitution. For example, if you consider the function f of x equals sine x over x, we cannot find using algebraic substitution the value of this function at x equals 0. Because in this case, if you put x equals 0, you get 0 over 0, which is meaningless. But if you graph this function, because you can substitute with any value very close to 0, you can substitute with any value which is very close to 0. So we can find this graph. We can find the graph of this function. And from this graph, there is high evidence that this function approaches this function approaches 1 when x approaches 0. We cannot say that f of x equal 1, but it seems that it is very close to 1 when x is very close to 0. So we write limit sine x over x as x approaches 0 equal 1 based on this graph which is obtained using numerical substitution. So this is the meaning or definition of the limit. We say that the limit of some function f of x equal L when x tends to a, and this mean the function can be we can make this function very close to L by making the independent variable x very close to a. And so in this case we say that f of x approaches L as x approaches a, or the limit of f of x equal L when x tends to a. Let's consider some examples and see how to solve this example, and also consider some cases that cannot be solved and we cannot find the limit using simple calculations or simple manipulation. This is a typical example in limits, how to find the limit. First of all, we substitute. Always when we solve a limit problem, we start by substituting. If the function is defined at this point, so this is the limit. But if we have some form of 0 over 0 or infinity, we have to investigate what is the limit of the function at this point. If you put x equal 3, you find it is 0 over 0. How to deal with this? Very simple. We can now factorize the numerator and then we can cancel this bracket with this bracket. So the remaining function is x plus 3. And this function is defined at x equal 3. Then the result equals 6. So this is the limit of this function at x tends to 3. Consider another example. In this case, we have limit tan x over x. We assume that we have the rule sine x over x, its limit equal 1 when x tends to 0. But now we have tan. We can write tan as sine over cosine. And in this case, we can say that the limit now is the limit of a product. We can distribute the limit by taking the limit of this expression, the limit of this expression, and then multiply the result. The limit of this expression based on the famous rule, it will be 1. And the limit of this expression by direct substitution also equal 1. So the result will be 1 times 1, which is 1. Also, if we have sine to x over x, we cannot apply directly the rule sine x over x, its limit equal 1 when x tends to 0, because here we have 2x and here we have only x. So we have to modify this x to be 2x. It's very simple. We can multiply by 2 and divide by 2. So in this case, we have a scaling factor 2. We can bring this scalar outside the limit and say that this is equal to 2 times the limit of this function. And the limit of the function is sine 2x over 2x, and you can say that when x tends to 0, also 2x tends to 0. So we can say that we have sine 2x over 2x when 2x tends to 0, which is equivalent to saying, for example, saying sine theta over theta when theta tends to 0. So it will be 1. So it is 2 times 1. But so based on this simple example, we can review some general limits governing finding the limit. We can distribute the limit over addition, over subtraction, over multiplication, over division, assuming the denominator is not 0, and also we have a constant multiplied by a function. We can bring this constant outside the limit. And also if we have some function based to some power n, we can bring this limit inside the bracket. So we take first the limit of this function and then take the result to the power n. And actually this is because this power function is a continuous function. The power function in general is a continuous function, and in general we can bring this limiting operation inside any continuous function. For example, sine or len is continuous function. So we can, for example, if we have something like this, if we want to find the limit, and we are going to do something like this at the end, we want to find the limit of len some function f(x). We can start by finding the limit and then take the limit. We can interchange limit and len. Why? Because len is a continuous function. We can say that this equal len limit f of x. We start by finding the limit of f of x and then take the len of z. This is correct because the len is a continuous function. And this is similar to what we have done here. Because the power function is a continuous function, we can take the limit inside the function. If you consider another example, if we have this function 1 over x minus 2 as x tends to 2. In this case, by direct substitution we find it is 1 over 0. This means that this function increases without bound when x approaches 2. And in this case, we say that this function, when we substitute x equal 2, we find it is 1 over 0. And this means that this function increases without bound when x approaches 2. So we say in this case the limit equal infinity. Actually, infinity is not a specific real number, but it is only an indication that this function increases without bound when x approaches 2. We don't need any further investigation. The problem has completed now. We have known the behavior of the function as x approaches 2. The function increases without bound. But if we get 0 over 0, we have to make further investigation to arrive at the conclusion what is the behavior of the function at this point. But if it is infinity, the problem is solved now. The function increases without bound. If you consider this example and substitute x equal 1, we find that the numerator equal len 1, which is 0, and the denominator is 1 minus 1, which is also 0. So we have 0 over 0. But how to solve this problem and how to find the behavior of this function as x approaches 1? In this case, we have to find some way to solve this problem. It cannot be solved by approaches similar to this example. So such example is one of the example that show we should find another rule to evaluate the limit, and in this case it is very useful to use what's called L'Hopital rule. L'Hopital rule says, this is the first form of this rule, if we want to find the limit of f over g, and by direct substitution this limit is 0 over 0. So the function f equals 0 at x equal a, and also the function g equals 0 at x equal a. So by direct substitution it is 0 over 0. The rule says this limit equal another limit, which is the limit of f prime over g prime. So in order to evaluate this limit, which initially give 0 over 0, and this is a very important condition, This limit initially is 0 over 0. Then this limit can be calculated by considering another limit, which is the limit of this ratio f prime over g prime. So we differentiate the numerator separately, also differentiate the denominator separately, and then take the limit of this ratio f prime over g prime, and assuming of course that g prime is not 0. And also for the proof of the validity of this result, we have to consider or to assume that f and g are two differentiable functions that have first derivative and also second derivative. Let's consider some example. Let's start with this example, limit ln x over x minus 1, which we consider in some previous slide. If we put x equal 1, you get 0 over 0, because initially this is 0 over 0. We can apply now L'Hopital rule. When we apply L'Hopital rule, we take the derivative of ln x and derivative of x minus 1. This will be 1 over x, and this is 1. Now we take or compute the limit again. The limit can be computed by putting x equal 1. This will be 1, and also this will be 1, so the result is 1. We have solved the problem and know the behavior of this function as x approaches 1. Also for this example, if we put x equals 0, you get 1 minus 1, which is 0, 0 power 2, which is also 0. So it is 0 over 0. We can apply L'Hopital rule. We differentiate this to get e power x, differentiate this to get 2x. Now, if you want to find this limit, try substitute x equals 0, it will be 1 over 0, which is infinity. So the problem is solved now. This function increases without bound as x approaches 0. The limit does not exist. We don't have some specific real value that the function approaches it when x approaches 0. But we have answered the question, what is the behavior of the function? It increases without bound. Consider another example. This function also, when you substitute x equals 0, you get 0 over 0. So we can apply L'Hopital rule. Derivative of tan x equals x squared, derivative of x equal 1. Derivative of x power 3 equals 3x power 2. Now, if we put x equals 0 again, you get 0 over 0. This recommends that you have to apply L'Hopital rule again. But in general, we have a very important note here. If you want to apply L'Hopital rule, be careful. You have to make some simplification first of the function before applying L'Hopital rule again. Because if you not make this simplification, you may continue forever, get 0 over 0, 0 over 0, 0 over 0. So in this case, we try to make some simplification. Sec square minus 1 equal 10 square. So this is 10 square over x square. Actually, this problem can be solved by applying L'Hopital again, because it is 0 over 0. Or can simply be solved by considering this to be 10x over x all power 2. And then take the limit inside the power function. The limit of 10x over x is 1. So it is 1 power 2, which is 1 multiplied by 1/3. So the result is 1/3. We have here an important note that what is the meaning of find the limit of 0 over 0? In this case, we say that the numerator is a function that approaches 0. And also the denominator is a function approaching 0. What happened finally when this arrives at 0 or be very, very close to 0? And also for this. If this function approaches 0 faster than this function, the whole limit will be 0. Because this function, you can imagine that this function approaches now 0, and this is still some constant. So it is 0 over some constant, the result will be 0. But if this function is the one that approaches 0 first, then the result will be infinity, because it will be some constant over 0. If the rate of decrease of this function, for example, to approach 0 is greater than this, the rate of this function, then the result will be for this function. This function approaches 0 first, and the result will be infinity. But if the rate of decrease or the rate of approaching 0 for both function, the rates are comparable, then we have some compromise. We arrive at some point, not 0 and not infinity, as happened in this case and in this case. The rate of the two function approaching 0 is somehow comparable. So we arrive at this intermediate point between 0 and infinity. And also in this case, the rate at which the two functions, the rates at which the two function approach 0 are somehow comparable. So we arrive at this intermediate point. But in this case, we arrived at infinity because the rate of decrease or the rate of approaching 0 for this function is much greater than the rate of this function. So the result is for this side. So the result will be infinity. The denominator approaches 0 faster than the numerator, so the result is infinity. Now L'Hopital rule has another form. It can be applied to functions that are initially infinity over infinity. If we have this ratio f over g, and this function approaches infinity as x approaches a, and also this function approaches infinity as x equal a, you can apply the same rule. Differentiate f, differentiate g, and compute the limit again under similar conditions. Let's go to some examples. In this case, we want to find the limit of e power x over x squared as x approaches infinity. Clearly, when x approaches infinity, e power infinity is infinity. And also x squared approaches infinity as x approaches infinity. So we have infinity over infinity. We can apply L'Hopital rule now by differentiating. It is e power x over 2x. And it is again infinity over infinity. So we can apply L'Hopital rule again. Take care, you have to make some simplification if possible. Actually, in this case, we don't have some simplification. So we apply L'Hopital rule directly again. Differentiate both sides. Now, if you study the behavior at x approaches infinity, you find this is infinity and this is a constant. So the result is infinity. And in this case, you can say that this function approaches infinity faster than this function. And so the result is for this function, which is infinity. If it is the reverse, if this function approaches infinity faster, the result will be constant over infinity, which is 0. If the rates are comparable, the result will be some intermediate point between 0 and infinity. Consider this ratio, cotan x over ln x. Also, when x approaches 0, this will be infinity, and this also will be infinity. And take care of this positive sign because ln x is not defined for negative. So we differentiate now. This will be negative cos x squared, and this will, again, it is infinity over infinity. We have to make some simplification before applying L'Hopital rule again. So cos x squared can be written as 1 over sine squared, and 1 over x can be written as x. So it is now x over sine squared. Actually, it is 0 over 0. You can apply L'Hopital rule. It is 0 over 0. Or you can make some simplification as this. It is x over sine multiplied by 1 over sine. The limit of x over sine is 1. And 1 over sine is 1 over 0, which is infinity. So the final result is infinity with a negative sign, this negative sign. So the final result is negative infinity. So till now we have considered the basic forms of L'Hopital rule. How to find the behavior of some ratio that initially is 0 over 0 or initially infinity over infinity. How to find the behavior of this what's called indeterminate forms, 0 over 0 and infinity over infinity. But actually we have some other indeterminate form, and we can in general apply L'Hopital rule to investigate the behavior of the function having these forms. Actually we have 7 indeterminate forms. In addition to 0 over 0 and the infinity over infinity, we have also infinity minus infinity, 0 times infinity, 0 power 0, infinity power 0, and 1 power infinity. Infinity minus infinity is an indeterminate form because if this function approaches infinity first, the result will be infinity. But if this function approaches infinity first, the result will be negative infinity. If the rate of approaching infinity is somehow comparable, we arrive at some intermediate point between infinity and negative infinity. And also for this form, for example, 0 times infinity. If this function approaches 0 first, the result will be 0. If this function approaches infinity first, the result will be infinity. Otherwise, there will be a compromise. And similar interpretation can be given for these forms. And actually, in such forms, we can say that 0 over 0 is actually 0 over 0, sorry, is actually very close to saying that 0, it is 0 over 0. Because if we say, for example, 5 power 0 equal 1, this is because 5 over 0 is 5 over 5, which is 1. So when we say 0 power 0, you can imagine that this is very similar to saying it is 0 over 0. So it is indeterminate form. And similar interpretation can be given for infinity power 0. 1 power infinity also is another indeterminate form. Actually, by 1 power infinity, we saying that function approaching 1. Not 1 exactly. It is a function approaching 1. And the power is approaching infinity. If the base approaches 1 first, so it's 1 constant approach power any number, it will be 1. It is 1 raised to any finite number, it will be 1. So if the base approaches 1 first, it will be, the result will be 1. If the exponent approaches infinity first, it depends on this, the value of this function. If, for example, this function is still a fraction, for example, half, power infinity will be equal to 0. But it is, if it is a number greater than 1, for example, it is 3 over 2, power infinity, the result will be infinity. So 1 power infinity is indeterminate form. It depends on which arrive first, whether the function here approaches 1 first or the function here approaches infinity first. So these are the 7 indeterminate forms. We represent the example to solve the first 2 forms, and now we consider some example to solve the other forms. Actually, we are going to consider example for this case, the third case, and also example for this case, and a single example for these 3 cases, because the approach is similar for the 3 cases. Let's start with infinity over infinity. If you consider this function, this difference, you can easily see that this function approaches infinity as x approaches 1, and also this function approaches infinity as x approaches 1. So we have infinity minus infinity. In general, to deal with this problem, you have to collect these 2 fractions in single fraction. This is the first step in dealing with infinity over infinity, to collect these 2 fractions into a single fraction. So we start to make a common denominator, so we have this fraction. Now, if you put x equal 1, you get 0 over 0. So you can apply L'Hopital rule now. We differentiate both numerator and denominator to get this expression. You can simplify by cancelling this one with this one, you get this result. Now again, if you put x equal 1, you get again 0 over 0. So we have to apply L'Hopital rule again. If you apply L'Hopital rule, you get this fraction. And by simple substitution with x equal 1, the numerator will be 1 and the denominator will be 2. So the final answer is half. So this expression arrive at some compromise. Not infinity, not negative infinity, but it is half, because the rate at which this function approaches infinity and the rate at which this function approaches infinity is somehow compromised. So we arrive at this intermediate point. Now, second case, 0 times infinity. For example, x times then x. As x approaches 0, this will approach 0. And as x approaches 0, this will be infinity, or actually negative infinity. So in general, it is 0 times infinity. Let's remember that ln x takes this form. This is the shape of ln x. Intersects the x-axis at x equal 1. And as at x equal or approaches 0, the function approaches negative infinity. This is ln x. So now we have 0 times infinity. In general, to solve this problem, starting with 0 times infinity, we bring one of these 2 functions as the denominator. For example, we can convert x to be 1 over x in the denominator, or convert ln x to be 1 over ln x in the denominator. But in general, we take the function in the denominator that makes the derivative simple. We make the derivative simple because we are expecting to make derivative to apply L'Hopital rule. So we choose to bring x in the denominator. and writing it as 1 over x. It is much simpler in differentiation than ln x. Simpler than 1 over ln x. So now when x approaches 0, this will be infinity, and also this will be infinity, so we can apply L'Hopital rule. When you differentiate, we get this fraction. We can simplify this fraction to get this simple result, negative x. And as x approaches 0, so it will be 0. So the final answer is 0. You can see that initially we started with expression approaching 0 and another expression approaching infinity. But the final answer is 0, which means that the first expression reaches 0 faster than the second expression. So the result is for this side. The result will be finally 0. The last example is to consider this function x power sine x as x approaches 0. And in this case we have 0 power 0. And as I said, we are going to consider this example, and in a similar way you can deal with the remaining two forms, infinity power 0 and also 1 power infinity. We start here by trying to bring this sine x down, this power. If we take y to be the limit of this expression, this is the required result. Now we take ln of any logarithm, but ln is easier. We take ln of both sides. So this will be ln y and this will be ln the limit. Now we can bring this ln inside the limit because ln is a continuous function. We can bring the ln inside limit, or actually in general we can interchange ln with the limit because ln is a continuous function. So it will be the limit of this ln function. Now we can apply the famous rules of logarithmic function and write this as sine x times ln x. Now when x approaches 0, it will be 0 times infinity, this negative infinity. So it is 0 times infinity. So we deal with this as we did in the previous example. We have to bring one of these two functions in the denominator. We choose to bring sine x in the denominator, and it will be cosec x. Now when x approaches 0, this will be infinity, and also this will be infinity. So we can apply L'Hopital rule now. We differentiate ln to get 1 over x, differentiate cosec to get negative cosec quotient. Now when x approaches 0, we can find this is infinity over infinity. But before applying L'Hopital rule again, we have to make some simplification. So this cosec quotient can be put in the numerator as sine 10, and this 1 over x can be put in the numerator as x. Now we can solve this limit very simple. It is sine x over x multiplied by tan x. And the limit of this will be 1. The limit of this will be also, the limit of this will be 1, but the limit of this function will be 0. So the final answer is 0. Take care now, this 0 is ln y. It is not the y. We need y, but this is ln y. So the final answer is y equal e to the power 0. Don't forget this important final step. We have got ln y. We need y now, which is the limit. So y will be e to the power 0, which is 1. So the final answer is 1. That's all for the applying L'Hopital rule for this case, and also for the similar cases containing power. We apply this example or consider this approach for 0 power 0, but you have to apply similar approach for infinity power 0 and also for 1 power infinity. That's all about L'Hopital rule and how to apply it to find the limit of some functions that start by indeterminate form. That's all. Thank you very much.